Gané! Yes! Ernesto, can you feel it?
Feel what, David?
The force of attraction between us.
Are you, feeling alright?
Not the attraction, Luso. I'm talking about gravitation.
Gravitation? What is that?
Oh, Ernesto. Puro SAT. So much to learn. You have so much to learn, man. I know you will tell us. Follow me.
So where are we going, David?
We're going to the NASA. The scientists will explain us what gravitation really means.
3, 2, 1. Main engine start, 0, and liftoff.
In order to understand gravitation, we became NASA scientists and armed ourselves with the knowledge of the universe. From our everyday experiences, we know that there's an ubiquitous force that brings us down to the surface of the Earth. We learn to call it gravity. However, sometimes that we cannot see in the day-to-day activities is that this force not exclusive to the Earth, but is true for every single mass.
Gravitation, or gravity, is the natural phenomenon by which physical bodies attract each other with a force proportional to their masses and inversely proportional to the square of the distance between them.
From what we learned here at NASA, we know that Sir Isaac Newton, based on the research of previous scientists, came up with the law of universal gravitation, which is F is equal to G, m1 times m2 divided by r to the power of 2, where F is the force of gravitation in newtons, m1 is the mass of the first object, and m2 is the mass of the second object. Both are in kilograms. R is the distance between the centers of both objects in meters, and G is a gravitational constant, approximately equal to 6.67 × 10 to the negative 11. The most essential part of this formula is G, which concretely defines how large of the magnitude of the force is. However, Newton did not find the exact value of G, he merely derived the proportion. That is, he said the force was proportional to some constant G. We will find that constant in this experiment. We will use a small light spring, some salt, a ruler, a balance, a light metal rod of each 0.5 meters, 2 small metal spheres, each 0.5 kilograms, a nylon wire, and 280 kilograms of gym weights. We will demonstrate that G is equal to 6.74 times 10 to the negative 11 by conducting an experiment called a Cavendish experiment, where 2 equal masses are placed on the opposite end of a rod, suspended from the center of mass and allowed to rotate in a horizontal plane. 2 more larger and equal masses will be placed in the horizontal plane at the same distance from the smaller masses, respectively. If the universal gravitation is true, then the rod should rotate towards the larger masses under the force of gravitation solely. Measuring the linear displacement of the spheres, the constant of gravitation can be calculated, proving or disproving the law of universal gravitation. Houston, are you there, Houston? We have a problem. We had some difficulty in setting up the machine. Firstly, we had to make sure there was no objects near it that could exert gravitational force on it. To do correct it, we set up on an empty room without shelves in. Secondly, we needed to make sure there was no air moving in the room, so we moved the balance. To fix this, we closed off the room and turned the air conditioner off, so there was no movement of air. Finally, we had the problem of the large masses. The first one we used were too small. They were 2 lead spheres. We used some bigger rocks, but they were still too small. Finally, we used some large gym weights that provided enough mass to exert a gravitational force.
On the screen, we can see the values for the materials we used in the experiment. The first step was to use the light spring and add masses to it. Salt was measured and then used. So we could find the spring constant and use it as a known force in order to find the torsion coefficient. The spring constant K is equal to mg over x. The data can be seen in the table. As we can see, the average spring constant found was 0.659 newtons per meter. To find the torsion coefficient, we create a torque diagram and add the forces involved in order to find it. K theta minus K of the spring XL divided by 2 is equal to 0. Solving for the torsion coefficient, K torsion is equal to K spring XL divided by 2 theta. Substituting the known values and the displacement recorded and the rotation, we get that K theta is equal to 0.047. We create an imaginary triangle using the radius of the rod as the two sides, the displacement as the third side, and the angle of rotation which we will find as the side opposite of the displacement. The law of cosines, which is c squared is equal to a squared plus b squared minus 2ab cosine theta. Simplifying for the angle yields theta is equal to arc cosine of a squared plus b squared minus c squared over 2ab. Substituting, we find that theta is equal to 0.004 radians. Now that we know all the variables we needed, including k, theta, r squared, L, m1 and m2, we can substitute them into the simplified equation for g and find that it yields a result of 2.69 times 10 to the negative 7 Newton meter squared divided by kilogram squared.
Touchdown confirmed. We're safe on live.
Using the formula for percent error and comparing our value with the actual value of g, we get a percent error of 403,000.
Even though there were difficulties in the setup and construction we attempted to fix, the experiment was conducted as stated in the procedures. The constant for the small spring and the wire were both found, and later the displacement of the small spheres measured. Calculating any values necessary in the function are shown in calculating and substituting them for the simplified formula for g. Yields the value of g equals 2.69 times 10 to the negative 7. Actually, getting a result is a success in itself. However, when compared to the actual value we needed, 6.767 times 10 to the negative 11, it is actually very wrong. It yielded a percent error of 400,000 and 198%. Consider the desired value is very small. A small deviation yields a large percent error. However, it still means our project did not achieve the goal of finding G.
The problem we faced was that the masses we used were exerted a very small gravitational force. In order to better conduct this project, more sensitive machines are needed that can easily detect the incredibly small movement caused by these very weak forces. The other alternative would be to use very large masses, as in billions of kilograms, in order to effectively see the force exerted. This would also require that the masses be very dense to avoid spatial constraints. To sum it up, we did not have the resources to conduct this lab appropriately. It did, however, show us how gravity and gravitation occur between objects in this universe, and this is a key concept for the study of space and possibly future space travel.
We would like to thank the following sources
For their explanation, design, and the idea for this experiment. Thank you very much.